Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be looking at the Southwest Regional Mock of 2023 Chemistry Paper 2. We are going to be answering section C, which is organic chemistry. So generally organic chemistry, we have 2 questions and it's always the last section. So guys, organic chemistry is not that easy as well as it is that easy, so it's just ironical because we usually term it volatile chemistry. Once you read it now, in the next 1 hour or in the least possible time you want to revise it, you definitely see that you never understood what you read, because we are not going to answer questions placed in front of you. Anyways, in the next video I'm going to be uploading, I'm going to give you tips and strategies on how to study organic chemistry. Okay, so if you're new to this channel, make sure you subscribe to the channel. If you have been there already, you know what we do. We like the video, we comment, and we share the video. So guys, let's get started with this particular video. Okay, so like I said, there are always 2 questions in organic chemistry. Question 5 and question 6 is always section C. So what we are going to be doing is that I'm going to display the question to you, and then I analyze the question and then I give you the solution. So if you have any worry, make sure you comment in the comment section. In fact, this is one of the videos where I want the audience to be very active. Okay, so I'm going to be posing some questions at some moments where you watching the video, you have to answer the question in the comment section. All right, because to make the video to be a little bit shorter, I'm not supposed to explain everything. So but I'm going to draw your attentions to so many things which, if not explained, I will just tell you to read on it and maybe give your answer in the comment section. So make sure you have a pen and a paper, where once I display a question to you, you try to answer the question by yourself. Then that is after pausing the video, you answer the question by yourself. Then afterwards you now play the video to see how I analyze a question and to see if your own answer is correct. So in case of me posing a question to you watching, make sure if you know the answer, you put your answer, you just type out your answer in the comment section and you send as a comment. Okay, I'm going to come and like it if it is correct, or I dislike it if it is wrong, and then give you the correct answer. All right, so guys, let's move on to what we have for today. All right, so here is question 5a. Briefly describe how the presence of the following elements can be determined in an organic compound after the sodium fusion test. So the very first question I want you guys to answer in the comment section is, what is the sodium fusion test all about? Why do we perform the sodium fusion test most at times, if not all the time? Okay, so tell me what you know about the sodium fusion test. That's how we analyze organic chemistry. Anyways, how do I identify the presence of iodine and the presence of nitrogen in an organic compound after performing the sodium fusion test? Let us begin with iodine. So I'm going to give you the reagent, that is the reagent you're going to be using, or I can say the substance you're going to be using, and I'm going to give you the observable change that will help you identify the presence of the element iodine. So to detect the presence of iodine in an organic compound, we start by adding acidified silver nitrate to the filtrate of the organic compound. When we do that, we are going to get a yellow precipitate, which is indicating the presence of the iodide ion. And if the iodide ion is present, then we can confidently say that the element iodine is present in the organic compound. What about nitrogen? For nitrogen, after performing a sodium fusion test, we now need to boil the filtrate with some iron sulfate, and also we add concentrated sulfuric acid. What happens is that a deep blue precipitate will be formed, which confirms the presence of the cyanide ion. And when the cyanide ion is present, then the element nitrogen is present in the organic compound. So guys, remember my question: define or explain or describe the sodium fusion test. What is a sodium fusion test all about, and what is the importance of the sodium fusion test? I'm waiting for your comments in the comment section. Okay, so that was A, Roman 1 and Roman 2. Let's move on to B. So question B, Roman 1, the enthalpies of hydrogenation of cyclohexene and real benzene are negative 120 kilojoules per mole and negative 208 kilojoules per mole respectively. So the first question is asking us to explain why the enthalpy of hydrogenation of real benzene is not 3 times that of cyclohexene. Now the second question I'm going to pose to you is define enthalpy change of hydrogenation. Actually, in thermochemistry or in energetics, there are so many enthalpy changes. We have enthalpy change of neutralization, enthalpy change of the reaction, enthalpy change of combustion, enthalpy change of atomization, and so on. And so we have electron affinity, and so on and so forth. And enthalpy change of hydration as well. Lattice energy also enthalpy change of hydrogenation. So what is the enthalpy change of hydrogenation of a compound? That is a question. Make sure you answer this question in the comment section. Okay, from there you are going to learn more. If your answer is wrong, I'm not going to say that. I'm just going to reply to you telling you that no, this is the correct way of putting it. Or if you have not used the right words as per the GCE, as per the advanced level chemistry GCE syllabus, then I'm going to explain to you the right words to use. Okay, so we need to explain why the enthalpy change of hydrogenation of real benzene is not 3 times that of cyclohexene. Anyways, let me first of all explain to you guys the principle behind this question. All right, so when you study organic chemistry and you go to the calculus or the evidence, or the I think when you go to aromatic hydrocarbons, where you have the benzene molecule as the reference point, you usually see 2 structures of benzene. We have the calculus structure of benzene and also the structure that contains the delocalized C electrons. So there are evidence that have proven which structure is the best structure, and in one of the evidences they talked about why the enthalpy change of hydrogenation of real benzene is not 3 times that of cyclohexene. They talked about the resonance structures. All right, so anyways, for a brief description, enthalpy change of hydrogenation is just the hydrogenation. I'm not going to define enthalpy change of hydrogenation because it's like I'm answering your question for you. I'm just going to explain what hydrogenation means. Hydrogenation means that we are adding the hydrogen molecule to a compound. Okay, so if I want to hydrogenate, let's begin with cyclohexene. Cyclohexene is an alkene. It's an alkene, right? And we know that the only difference between alkanes and their corresponding alkenes is the difference in the number of hydrogen atoms. Alkenes have 2 hydrogen atoms less than their corresponding alkenes. So if I take ethane and ethene, ethane has 6 hydrogen carbons and ethene has 4 hydrogen carbons, so the difference is 2. Both of them have 2 carbon atoms, so that's why I'm saying corresponding. If I take propane and propene, the number of carbon atoms are the same, but there's just 2 hydrogen atoms that are lacking in ethene, in propene, to make it propane. So if I want to hydrogenate cyclohexene, it means that I'm going to add the hydrogen molecule to it, which is actually H2. And adding H2, you realize that you're going to take it to its corresponding alkane, which is now cyclohexane, because the only difference between this cyclohexene and cyclohexane is a difference in the number of hydrogen atoms. So if I am adding the 2 hydrogen atoms back to cyclohexene, definitely I will get cyclohexane. So when I hydrogenate cyclohexane, I get cyclohexane, and the enthalpy change accompanying this reaction is called the enthalpy change of hydrogenation of cyclohexane. Now let us talk about the Kekulé structure of benzene, where we have benzene having 3 double bonds alternating with 3 single bonds. So if you want to hydrogenate, basically we need a balanced equation where we are going to instead of adding hydrogen here, we are going to add hydrogen, and we are going to have cyclohexane. But now to balance the equation, we need 3 hydrogen atoms. So when we add 3 hydrogen atoms to the Kekulé structure of benzene, this is not the real structure, right? And the evidence is clear. So when we add 3 hydrogen atoms, when we add 3 hydrogen, the 3 hydrogen molecule, which is basically 6 hydrogen atoms, yes, 6 hydrogen atoms onto the Kekulé structure of benzene, we are definitely going to have cyclohexane, and the enthalpy change accompanying this reaction should normally be 3 times the enthalpy change accompanying this reaction, because in this reaction we are just adding 2 hydrogen atoms, but here we are adding 6 hydrogen atoms. And adding 2 hydrogen atoms means we are adding the hydrogen molecule, and here we are adding 3 of the hydrogen molecule. So the enthalpy change accompanying the second reaction should just be 3 times the enthalpy change accompanying the first reaction. All right, but now the thing is that real benzene has this structure. This is the structure of real benzene. So automatically, why is it that the enthalpy change of hydrogenation of real benzene, which is this, is not 3 times that of cyclohexane? It is clear the real structure of benzene is not containing 3 double bonds alternating with 3 single bonds, right? Because if it is containing 3 double bonds alternating with 3 single bonds, then definitely the enthalpy change of hydrogenation will be 3 times that of hydrogenation of cyclohexane. But because it does not contain, since this is not the real structure of benzene, then remember this is a real structure of benzene. Okay, so the answer is the real structure of benzene does not consist of 3 double bonds alternating with 3 single bonds. Like I said, if this was a real structure of benzene, then automatically the enthalpy change accompanying this reaction will be 3 times the enthalpy change accompanying this reaction. But because this is not the real structure of benzene, then the enthalpy change accompanying this reaction will not be 3 times the enthalpy change accompanying this reaction, having in mind that the real structure of benzene is this structure having a delocalized C electrons, and it does not have 3 double bonds alternating with 3 single bonds. So guys, make sure before you are leaving this slide, before I am going to the next slide, you have answered what enthalpy change of hydrogenation is. Okay, now the second part of the equation is asking us to calculate the resonance or the delocalization energy of benzene. So what is the resonance energy of, or the delocalization, or in fact we can also call it the stabilization energy of benzene? It is basically the energy that will convert benzene from the Kekulé structure to the real structure. We saw that the Kekulé structure will have 3 double bonds alternating with 3 single bonds, but the real structure will have a delocalized C electrons, right? So the energy involved in converting that Kekulé structure to the real structure is what we call the stabilization energy, or the resonance energy, or the delocalization energy. I'm going to explain briefly using Hess's law. All right, so let us first of all begin with the first structure, the first equation, where we are actually hydrogenating cyclohexane. So hydrogenating cyclohexane, like I explained previously, we need to add the hydrogen molecule to it. We are going to get cyclohexane. We can call the enthalpy change accompanying this reaction to be delta HR1. Okay, now let's consider now converting the Kekulé structure, that is hydrogenating the Kekulé structure of benzene. So hydrogenating the Kekulé structure of benzene, we need to take the Kekulé structure of benzene and then we add 3 hydrogen molecules to it. We are still going to have cyclohexane. The enthalpy change accompanying this reaction, we saw that it is 3 times the enthalpy change accompanying the first reaction. All right, now let's now see how we can convert real benzene to real benzene to cyclohexene, that is hydrogenating real benzene. So if I want to move from real benzene onto cyclohexane, the enthalpy change accompanying the reaction, I can call it delta HRO2. That is what I'm going to have. All right, so this is the hydrogenation of real benzene. The value of this was given, so we can definitely get the value of this. But now, according to Hess's law, no matter the path taken from the reactants to the products, the path taken does not matter. The path taken accompanying the enthalpy change accompanying the chemical reaction does not change, provided the path taken from reactants to products at physical conditions is maintained. So basically, that's, I'm just paraphrasing Hess's law. So in Hess's law, remember that the main objective is actually to convert the energy we are looking for is the resonance energy, meaning the energy needed to convert this calculated structure of benzene to the stable structure of benzene, or the real structure of benzene. This is the energy we are looking for. We can call it delta HRO4. But now I can use an intermediate compound, which is the cyclohexane, right? Because you see that we can convert this to cyclohexane as well as we can convert this to cyclohexane. So if I decide to convert the calculated structure of benzene to cyclohexane, the enthalpy change involved is delta HRO3. Or if I decide to convert the real benzene to cyclohexane, the enthalpy change involved is delta HRO2. Hess's law says that the enthalpy change accompanying a chemical reaction, the enthalpy change accompanying this chemical reaction, basically from Hess's law, delta HRO4 plus delta HRO2 should give us delta HRO3. Why? Because delta HRO4 and delta HRO2 are kind of are in the same direction. Let me put it that way. You see, if I begin from here and I'm going this way, I'll continue going this way. The arrows are pointing in the same direction. But when I come here, this arrow is reversed. That's why I need to sum all the arrows going in the same direction and I equate to the sum of all the arrows going in the opposite direction. We just have one arrow going in the opposite direction. So basically, this plus this should give us this. You see, this direction is reversing my original direction. Okay, so that is what Hess's law is saying. So from here, we know that delta HRO3 is 3 times delta HRO1. It therefore means that if I want to look for delta HRO4, I'm going to subtract delta HRO2 on both sides. Then I replace delta HRO3 with 3 times delta HRO1. So the enthalpy change accompanying this reaction, which is actually the delocalization energy of benzene, is basically gotten by taking 3 times the enthalpy change of hydrogenation of cyclohexane. Then we subtract the hydrogenation, the enthalpy change of hydrogenation of real benzene. We are going to get the delocalization energy. That is the energy involved in stabilizing the benzene molecule, the benzene compound. All right, so from there, that's what Hess's law is saying. Now, originally in the equation, we have the enthalpy change. We have the enthalpy change of hydrogenation of cyclohexane. That was delta HRO1. We also have the enthalpy change of hydrogenation of real benzene. That is delta HRO2. So basically, the energy that is used in stabilizing the benzene molecule is what we call the resonance energy, or the stabilization energy, or the delocalization energy. So from here, if I want to find it, I need to take 3 times negative 120 to give me negative 360 minus negative 208. Simplifying, we are going to get that the resonance energy of benzene is negative 152 kilojoules per mole. So the energy involved in stabilizing the benzene compound is negative 152 kilojoules per mole. That's it for the equation. If you got it right, confirm. Okay, next question. In not more than 2 steps, write equations to show how benzoic acid can be obtained from benzene. So this hydrogenation is not supposed to be there. Okay, I think it's a typing error I did, so cancel hydrogenation. So in not more than 2 steps, write equations to show how benzoic acid can be obtained from benzene. Okay, So if you are done writing, then watch. Remember, in not more than 2 steps. So maximum should be 2 steps. Though you can use 1 step. Yeah, I don't think it is possible to use 1 step. If it was phenol, yes, we could use 1 step, but now it is benzene. So I need to get an intermediate. So I need to convert the benzene to a certain compound. Now converting to benzoic acid is actually oxidation. That's the first thing I think of, oxidizing a certain compound to give me benzoic acid, because benzoic acid is a carboxylic acid. So which compound will I be able to oxidize to get benzoic acid? The first thing that should come to your mind is toluene, that is methyl benzene. If you have studied the benzene and you see the reactions, you're going to know exactly what to do here. So the first thing to do is that I begin with my benzene molecule. Then from there I need to convert it to methyl benzene. Okay, and what do I need to convert benzene to methyl benzene? I undergo so my first question is the process called the alkylation of benzene or the acylation of benzene. That is my question. So write your answer. If I add chloromethane, this is aluminium chloride and a reflux. Okay, is aluminium chloride is this reaction the acylation of benzene or the alkylation of benzene? Now, is it also, which type of reaction is this? Is it electrophilic substitution? Is it electrophilic addition, and so on and so forth? Those are the things that you need to understand. Also, can you write down the mechanism of this reaction? Very important questions you have to answer in the comment section, so that in the next video I'm going to know what I'm going to be doing, okay, based on your difficulties. All right, so if I add this reagent and reflux, I'm going to get toluene, which is methyl benzene. Now if I oxidize methyl benzene, I'm going to get a carboxylic acid, which is basically benzoic acid. But what do I need to oxidize methyl benzene? I need a very strong oxidizing agent that will take it directly to benzoic acid, because sometimes you can use a reagent and it's going to produce a certain compound before taking it. So that's why we need a very strong oxidizing agent, and basically a very strong oxidizing agent that we convert it directly to a carboxylic acid is acidified potassium permanganate. So this MnO4- is just the permanganate ion, and then now H+ identifies that this is acidified. H+ is for acid. All right, so this acidified potassium permanganate, and under reflux, that's my reaction condition. So doing this, you see, maximum 2 steps, I have converted benzene to benzoic acid. Okay, as we move ahead, questions become interesting and interesting and interesting. If the video is interesting to you as well, make sure you like the video as you watch. Okay, liking the video is very important. Okay, study the synthetic pathway below and answer the questions that follow. Here we have a synthetic route where we move from compound A to compound B. Now compound B can give you 2 different routes, compound C and compound F. Then compound C goes to D and E and I, and F goes to G, H and I again. So at the end of the day, we need to move from A right up till I using 2 different pathways. That's the essence of the equation. All right, so without wasting much of your time, let's just go straight away into answering the questions. Let's forget about studying the whole synthetic route. I think answering the questions will give us a better understanding of studying detailing this synthetic route. All right, now Roman 1 says write the systematic name of lactic acid. This is lactic acid. Lactic acid is basically, I can say, the scientific name or the common name of this compound, but the systematic name of a compound is gotten via naming the compound using the IUPAC way of naming. Okay, so I need to name this compound using the following rules of IUPAC. So first of all, there are 2 functional groups here. If you look at it clearly, we have the alcoholic functional group and we have the OH group, and then we have the COOH group. this COOH is the carboxyl group and OH is the hydroxyl group, right? So the first thing is we need to identify, is this an alcohol or is a carboxylic acid? Anyways, it's very clear, lactic acid, so it is a carboxylic acid. Therefore this OH group here will be a substituent group. Okay, if it was an alcohol, it's going to end with all, right? It's going to end with all. If it's a carboxylic acid, it will end with something oic acid, right? But between a carboxylic and OH group, the carboxylic is more open to reactions, like it is more reactive than the OH. So from there you clearly realize that the main functional group here will be the carboxyl functional group. And from there, to name this compound, we now need to begin by looking the number of carbon atoms. There are 3 carbon atoms. Now the OH group is attached to which carbon atom? To carbon atom number 2. Therefore, since the OH group here is not the main functional group, then we say hydroxy, not hydroxyl. No, it is hydroxy. There is no L at the end. Many people make that mistake. So this compound OH is attached to carbon number 2. It therefore means that we are going to call it 2-hydroxy. Now, how many carbon atoms are here? There are 3 carbon atoms, and the main group here is the carboxylic functional group. So it's going to end with oic acid. And since it is 3 carbon atoms, then it is propanoic acid. So the best name given to this is 2-hydroxy propanoic acid. Okay, Roman 2. If compound B has a relative molecular mass of 64.5 and it consists of carbon, hydrogen and chlorine only, remember only, determine the structure of B. Now this question was very technical when I was about to answer, so I want you to pay very keen attention to what I'm about to say, because guys, if you are not able to solve question B, the rest of the questions will be impossible for you to solve, because compound B is like the king here. Once you have it wrongly, the F and H will be wrong, D and E will be wrong. So to pass this question, you must pass compound B. So that's the secret behind this question. To pass this question, you must pass compound B. Now, I have a very strange analysis, but I don't know if it's strange here, but it's very logical as well. And I'm pleading that if somebody else has another methodology or another method of getting compound or getting the structure of compound B, make sure you tell us in the comment section. We are going to learn. Okay, so if my methodology is not really convincing for you, though I think it's going to be convincing, but if it is not really convincing for you, then make sure you tell us what you have in mind. Okay, but trust me, after having my compound B from my methodology, I could easily get the other compounds, and the synthetic route was very okay and complete. So anyways, the compound I'm going to have at the end of the day, if you have another way of getting to that compound, you tell us. We are going to be interested in learning your method. Very important, we learn every day. Okay, not that the method I use must be the method you're going to use. Okay, so first of all, I came to this question, I was like, okay, I need to convert from an alkene, this is 18, to a compound. Now I need to leave that compound and I go to another compound. So my main reference is first of all this compound here. Okay, my main reference is this compound. This compound has 3 carbon atoms. Wow, having 3 carbon atoms, I could leave from a compound having 2 carbon atoms to a compound having 3 carbon atoms. Yes, or I could also leave from a compound having 3 carbon atoms to a compound having 3 carbon atoms. Yes, but now look at, I'm beginning from a compound having 2 carbon atoms. It therefore means that the best structure for compound B should be a compound having 2 carbon atoms. Before now I start, because it is easier to add. Remember that compound B has carbon, hydrogen and chlorine. It is easier to substitute chlorine with a carbon atom. Yes, very easy to do that. Okay, than to break this double bond and have 3 carbon atoms. Okay, also look at, if compound B has 3 carbon atoms, then it means that compound F will also have 3 carbon atoms. Okay, and compound F having 3 carbon atoms, then I'm adding this man because here this guy is going to have 2 carbon atoms, and it is not possible to oxidize something with 3 carbon atoms and get 2 carbon atoms. Okay, because when we are oxidizing, this is acidified potassium dichromate, we are not increasing or decreasing the number of carbon atoms. So my second reference was now compound G. Compound G has 2 carbon atoms, and oxidizing a certain compound to compound G, this compound here must have 2 carbon atoms, because this oxidizing agent does not decrease or increase the number of carbon atoms, it allows the number of carbon atoms as they are. So it means that compound F must have 2 carbon atoms. Now, compound F having 2 carbon atoms, it therefore means that compound B will also have 2 carbon atoms. Okay, or anyways, compound B could also have 3 carbon atoms, and we convert it to a compound having 3 carbon atoms. But when we are converting compound B to compound F, since compound B is having 3 carbon atoms, then compound F is supposed to have 2 carbon atoms, so that when it's going here there are 2 carbon atoms. But anyways, the best way I thought of it is let compound B have 2 carbon atoms, then everything is going to be perfect. Okay, all right. So since compound B has carbon, hydrogen, and chlorine, it therefore means that compound B basically has 2 parts. It has an alkyl part and it has the chlorine part. Because this alkyl part, remember what is R? R is an alkyl group. Cl is chlorine. And what is an alkyl group? An alkyl group is basically an alkane molecule that has lost a hydrogen atom. So if I begin with methane, methane is CH4. So if I want to get an alkyl group, calling it methyl, I'm going to have CH3. I just need to remove one hydrogen atom from methane, and so on and so forth. We are going to see that later. Okay, so this is the supposed structure of my compound B. Okay, now I need to calculate the relative molecular mass of the alkyl group, because I know the relative molecular mass of chlorine. So since the compound contains carbon, hydrogen, and chlorine, it therefore means that it contains this alkyl group and chlorine. So the relative molecular mass of the alkyl group should be the relative molecular mass of the whole compound, which is 64.5, minus that of chlorine. Subtracting that, you get 29. That is the relative molecular mass of the alkyl group. Now let us name some alkyl groups we have. We have the methyl group, which is methane losing a hydrogen. We have the ethyl group, which is ethane losing a hydrogen. We have the propyl group, which is propane losing a hydrogen, and so on and so forth. Now let's try to look for their relative molecular masses. So this man is going to be 12 plus 3, which is giving us 15. So R can never be methyl. Now what about this man? You have CH3 is 12, then CH3 is 15, C is 12. When you add 15 to 12, you get 27, and then H2 is 2. 27 plus 2, 29. You now see that perfectly the alkyl group in this question is what? The ethyl group, CH3, CH2. So that is R. And having this as R, we can now deduce a compound B. That a compound B is CH3, CH2, Cl. What is the name of this compound? The name of this compound is... Yes, I'm waiting for you. Comment section. Okay, I'm not going to answer. Tell me the name of this compound in the comment section. The name of this compound B. Just give us a name. Alright, so the next part is saying that identify C by structure and systematic name. So I'll first of all expand this man. Okay, I'll expand C. First of all, what is C? It's ending with nitrogen, so it's a nitrile. Okay, for those of you who have done nitrogen containing compounds, the amines, the nitriles, and all the rest. So C is the nitrile. So let us first of all expand. 3 carbon atoms, 5 hydrogen atoms. Carbon bonded to nitrogen will be a triple bond, because that's for the nitrile. Okay, now I've already used 1 hydrogen atom, so I need 4 more hydrogen atoms. So let us fill. Remember, carbon has to bond with a covalency of 4, so you need 4 covalent bonds. There are 3 already, and here 1, so we cannot attach a hydrogen atom again to this carbon. This carbon has 1, 2, 3. This carbon has 1, 2, 3, so we need 1 hydrogen atoms again. So we have the 2 arrows, the 2 lines, This for the first hydrogen atom, the second hydrogen atom. So this carbon here will not have an hydrogen atom. So a hydrogen atom. So if we count, we have 1, 2, 3 carbon atoms, 1 nitrogen atoms, and 1, 2, 3, 4, 5 hydrogen atoms. That is C3H5N. So this is a nitrile. So by the name, we are going to write it this way. That's a structure. And then now the name, how many carbon atoms, since you are naming it as a nitrile according to the IUPAC way of naming, okay, it's a nitrile. That's a main functional group. The other, we could also call it an alkane. All right, we can also call it an alkane molecule with the cyano group as a substituent. But that is going to be an isomer. Okay, that's going to be an isomer. But we need a systematic name. The nitrile is more is more open to attack, is more stable than the alkane. So we are going to call it a nitrile. Okay, so to call it a nitrile, this N is actually what is contributing to that word nitrile. So I need to count the number of carbon atoms here. 1, 2, 3. So there are 3 carbon atoms, and when there are 3 carbon atoms, we use prop. So it is propane nitrile. That is a systematic name, or we call it propanonitrile. Now, in other words, or maybe if we want to name it as a cyano, maybe if you're asking for an isomeric name, we are going to call it cyanoethane. We are going to combine C and N to call it cyano, and then now we don't count the C again as in when we are counting the number of carbon atoms. We just count the 2 C's here, and we just have eth, which is ethane. So we can call it cyanoethane, but the systematic name is propane nitrile. Propane for 3 carbon atoms, nitrile for this big man here. Okay, next question. State the reagents and the reaction conditions for preparing compound C from compound B. This is compound C. We have seen it already. It is propane nitrile or propanonitrile. We want to prepare it from compound B. What is compound B? I told you to put the name. I'm just going to give you the name. So compound B is specifically 1-chloroethane. Okay, 1-chloroethane. So I need to prepare propanonitrile from 1-chloroethane. Now, the first thing to realize is an increase in the number of carbon atoms from 2 to 3, and the replacement of the chlorine molecule, okay, by Cn or by N. So what do I need to increase the number of carbon atoms? That reagent is unique, it is standard. To increase the number of carbon atoms of a compound, this is basically what we need to do. We need to add sodium cyanide in ethanol, that is alcoholic sodium cyanide or alcoholic potassium cyanide. So we just need to add a cyanide, okay, a cyanide to it. So it's sodium cyanide, potassium cyanide, I think even magnesium cyanide will work. So sodium cyanide in ethanol is a reagent. We are going to increase the number of carbon atoms, and the condition is refluxing. Okay, that's Roman 3. Roman 4, give the structural formula of D, E, F, and H. Analyzation again. Let's go to D. Now, we know this man. This man is this man is propanitrile. Now let us look at the last compound. Okay, the last compound should be the bus stop. Then now we try to go backwards and start thinking. So this guy here has 3 carbon atoms. The last compound has 3 carbon atoms. So perfect. We are not increasing the number of carbon atoms again when we begin from C. Let's first of all go through this pathway. Okay, now this guy here is actually propanonitrile. How will I convert propanonitrile to a carboxylic acid in 2 steps? Because I need to move from C, but I need to pass through 2 different steps before I get to the carboxylic acid. So first of all, you need to think of removing the nitrogen. Okay, so what is the possible structure of compound of compound Z. So the possible structure of compound Z is converting this nitrile to a carboxylic acid directly. Okay, if we convert it to a carboxylic acid directly, then because normally we need to end with a carboxylic acid, so if we start by first of all converting this to a carboxylic acid, which is possible, okay, then we are going to have good results. Now, after converting it to a carboxylic acid, what do we need to convert it to again? We need to convert it now to a chlorocarboxylic acid. Why? Because see, we have an OH here, and if I introduce sodium hydroxide, okay, in this compound having this chlorine here, then the OH is going to replace chlorine, and then sodium will take the chlorine to produce sodium chloride. Okay, so that's how you start thinking. I first want it to move to a carboxylic acid, and then now I need to add something to the carboxylic acid to have a chlorocarboxylic acid, so that when I add something again to the chlorocarboxylic acid, and I have a hydroxycarboxylic acid. So to move from a nitrile to a carboxylic acid, that's the first question. What do we use? To move from the carboxylic acid to the 2-chloropropanoic acid, which is also the carboxylic acid, which reagent do we use? That's the second question. You have to answer in the comment section. Okay, if you don't know, run to your books now and check. I think if you run to your book and check, you'll never forget, because you always remember that I saw it in this video and I checked from my book. Okay, now let's go to F. So what is the possible structure of F? It's an alcohol, clearly, because if I oxidize to now let's go to G. G is an aldehyde. Clearly, it's an aldehyde if you expand the structure of G. So what do I oxidize to get an aldehyde? The first thought is a primary alcohol, which is going to have 2 carbon atoms, and clearly to convert from this 1-chloroethane to ethanol, what do I need to add? I need to add sodium hydroxide. That is aqueous sodium hydroxide. We call those are SN mechanisms. I think it is SN1, SN2 mechanism. No, SN1 mechanism, yes, since a primary alcohol. So if I convert this guy to an alcohol, then if I use potassium dichromate, acidified potassium dichromate on a primary alcohol, I get an aldehyde. Okay, but if I use acidified potassium permanganate on a primary alcohol, I am going to get a carboxylic acid directly. Okay, that is why we said acidified potassium permanganate is a very strong oxidizing agent. It does not give any intermediate, because to convert primary alcohols to carboxylic acid, we can either use excess potassium dichromate when we are putting it in excess. In fact, even if you put in excess, sometimes you'll not even convert it. That's why we just need, if it's one way, we can take it directly to a carboxylic acid using potassium, using acidified potassium permanganate. But if you want to use a 2-step method, we are going to convert it to an aldehyde. Then again, we oxidize the aldehyde to get a carboxylic acid. So F here is ethanol. Yes, ethanol. And what about H? Now H, remember, this is an aldehyde. All right, this is an aldehyde. So to get H, remember, you must convert this aldehyde to a carboxylic acid. Yes, so H is going to, or not necessarily a carboxylic acid, you must convert it to something that will be easily convertible to a carboxylic acid. All right, so you can convert it to a hydroxyl nitrile, so that when you oxidize, you get a carboxylic acid, which is the lactic acid. Okay, so guys, that is it for D, E, F, and H. Roman 4. The lactic acid prepared in a laboratory has an asymmetric carbon, but it is not optically active. Explain. First thing is that, what is an asymmetric carbon? It's a carbon that has 4 different groups bonded to it. Okay, that's an asymmetric carbon. Okay, so lactic acid prepared in the laboratory is actually a racemic mixture, and a racemic mixture is always optically inactive. Now rotate your phones. I've defined a racemic mixture here. Here's the definition. An equimolar mixture of two optically active isomers is called a racemate or a racemic mixture. So basically, lactic acid prepared in the laboratory is actually a racemic mixture, and a racemic mixture is optically inactive. That's a little explanation to this question. Roman 1. What spectroscopic techniques can be used to identify functional groups in an organic compound? First, we have infrared spectroscopy, and also we have the nuclear magnetic resonance spectroscopy. Roman 2. Write the structure of alanine. This is an amino acid in a neutral medium. For biology students, when you were doing biomolecules, I think you came across this. So first thing is that this guy here, okay, alanine, is actually amphoteric. Okay, it means that it exists both as an acid and a base. Okay, so if you want to write it, so in an acid medium is going to be acting as a base, while in a basic medium is going to be acting as an acid. So in a neutral medium is supposed to have those two components. And remember the definition of an acid by Bronsted and Lowry, also by Lewis. Then you're going to get that this is the required structure. So the definition of an acid, consider talking about the loss of hydrogen or the gain of oxygen and so on and so forth. Okay, so when you do that, you're going to get this structure as the structure of alanine in neutral medium. Like I said, it's amphoteric. It has both the acidic side and the basic side, acting both as an acid and a base. Like water can act as an acid when it has H plus and a base when with the OH minus. Okay, so that was that for question 5. Question 6, another journey again. This video is already 46 minutes 22 seconds. Anyways guys, just stay with me. Okay, stay with me. Okay, using question 6a, using suitable reagents and reaction conditions, show how you can distinguish between the following compounds in the laboratory. Roman 1. But1-ine, that is butane, where the triple bond is on carbon number 1, and but2-ine, that is still butane when the triple bond is on carbon number 2. The second one is propan-1-ol and propan-2-ol. This one is when the OH group is at the end. This one is when the OH group is at carbon number 2. So how do I distinguish between but1-ine and but2-ine? These are alkynes. Okay, the last types of hydrocarbons, alkynes. Now, how can I distinguish between two alkynes? First of all, I need to identify the type. We have a primary alkyne and we have a secondary alkyne. So how do I distinguish between two alkynes? Because actually, right, alkynes are unsaturated hydrocarbons. Okay, so they decolorize bromine water. So if I was distinguishing between an alkyne and another molecule that cannot decolorize bromine water, I'm just going to use that one. But now we have two alkynes, we need to distinguish between them. So follow keenly. So I'm going to give you the reagent and the reaction condition. So the reagent and the reaction condition is we need to add silver nitrate in ammonia at room temperature and pressure. What is the observation? What do I see that will be able to distinguish between the two? So the first compound will form a white precipitate, while the second compound will not give any observable change. Let's go to propan-1-ol and propan-2-ol. These are two alcohols. One is a primary alcohol and one is a secondary alcohol. So you need to ask yourself, which chemical test will I use to distinguish between a primary and a secondary alcohol? So basically, the reagent and reaction condition, we can use iodoform test. That is iodine in sodium hydroxide. What is the observable change? Propan-2-ol, which is a secondary alcohol, will give a yellow precipitate with an antiseptic smell, while propan-1-ol will not. So the next question I have for you guys is, what is this yellow precipitate called? Answer in the comment section. B, Using chemical equations, show how you can produce the following amines from propanamide. This is propanamide. So how will I produce an amine from propanamide? If your name is Amine, farewell. Okay, farewell to you. So you have to pass this equation if your name is Amine. So how do I produce an amine from propanamide? So the first amine is actually this. See, so we have 3 carbon atoms. So this is propylamine. Oh, okay, propylamine. Now the second amine is ethylamine. Now let's come back again. So I need to convert propanamide to ethylamine and also to propylamine. So I can say that this P here is a reaction, the reagent and the reaction condition, and this R here is a reagent and the reaction condition. So because we actually need to write equations, okay, but since I was not having space in this very slide, I tried to just write what P is and what R is. So let's analyze again. Propanamide is prop, it has 3 carbon atoms. Taking it to propylamine, we have 3 carbon atoms, so the number of carbon atoms stay intact, okay. But now what has happened? We don't have O again. Yes, we don't have O again, and since we don't have O again, you realize that we now have an H2. So remember, the only thing that's changed between these 2 compounds is the introduction of H2 and the removal of O. So what do I remove O with? It's like kind of I'm removing water, right? So I need to what? I need to dry. Like I need to introduce a drying agent. So basically I need to use lithium aluminum hydride in dry ether. All right, this is a dehydrating agent. It's going to remove this oxygen from here completely. We are going to get propylamine. Now what about the next guy? Here I'm also removing the O, as well as I am decreasing the number of carbon atoms. Remember, there are 3 carbon atoms in propanamide, but ethylamine has 2 carbon atoms. So previously I showed you how to increase the number of carbon atoms. So now I'm going to show you how to decrease the number of carbon atoms. So what do I use to decrease the number of carbon atoms? I need to first of all heat bromine in aqueous sodium hydroxide or aqueous potassium hydroxide. Is going to decrease the number of carbon atoms. So that is P and R. Now the next question is, how is a reaction in Roman 1b above called? Roman 1b is that what is the name of the reaction in converting an amide to an amine where the number of carbon atoms have been decreased? We call it the Hofmann's degradation. If your name is Hoffman, farewell to you. Make sure you don't fail this type of questions here, because you have actually written your name as Hoffman in your exam paper, and then there's a question asking you to rewrite your name. So don't make a mistake of filling this type of question in the exam. So that process is the Hofmann degradation reaction. Okay, so we are with slide 9. We have 3 more slides to go. Write the structure of the major product of the following reactions. I've not read this thing because I believe you guys can read it. You need to tell me in the comment section how the video is, if you need another video of such, and also please, if you have shared the video, comment that, say I have shared the video. I'll be very happy. Okay, write the structure of the major product of the following reactions. Roman 1, refluxing of aqueous sodium hydroxide with this compound. What is the name of this compound, guys? Like, I want this comment section to be very active if you are watching this video, and if you have watched till this length, 53 minutes already. It means that you are really interested. You really needed this video. So tell me the name of this compound. Okay, so if I reflux aqueous sodium hydroxide with this guy, what am I going to have? So basically we need to add, this is a halogenoalkane. Okay, we need to add it to aqueous sodium hydroxide. We are going to get an alcohol. When we reflux, we get an alcohol. Okay, the OH group will be replacing the bromine, so we are going to get a secondary alcohol. So this secondary alcohol, there 1, 2, 3, 4 carbon atoms, and OH is on carbon number 2. So it is since an alcohol, it is butanol. Yes, butanol. Now the second question is, if I reflux instead with alcoholic sodium hydroxide. First one was with aqueous sodium hydroxide. Now you're refluxing with alcoholic sodium hydroxide. You are not going to get an alcohol, please. You are rather going to get an alkene. Yes, you're going to get an alkene. So it's just bizarre. How can I reflux with aqueous, then I have an alcohol? Then instead reflux with alcoholic, then I don't have an alcohol. Anyways, when we reflux with alcoholic sodium hydroxide or potassium hydroxide or magnesium hydroxide, we get an alkene. This is but2ene. Okay, that's but2ene. The first one is butanol. Question Z. Given a compound, this is a compound. Let me help you name the compound. What is the name of this compound? Let me even help you. What's the name of this compound? I'm not supposed to help you. The main functional group is which group? That's the first question you should ask yourself. What is the main functional group? Is it OH or is it the carboxylic functional group? And after naming the compound, there's a question. How will you test for the presence of the following functional groups? The OH group, I highlighted, test for the hydroxyl group. So how will I test for the hydroxyl group? That is testing if a compound contains a hydroxyl group. It's a very basic test. Even you guys who you know where to find this test in your chongwa. What do I do? I need to react the compound with what? With PCl5. Okay. What's the observation? Dense white fumes of HCl gas is evolved. That's the observation. So PCl5, a very common test. So how do I test for the COOH group? That is the carboxy group. So what do I need to do? I need to add sodium hydrogen carbonate or sodium carbonate to the compound, and I'm going to get something. Effervescence. First of all, I did not put effervescence, but effervescence will occur. Then a production of a colorless, odorless gas, and this gas will turn lime water milky. So the next question I'm asking you is, what is the name of the gas that will turn lime water milky? Let me ask another one. What is the name of the gas that will rekindle a glowing spleen? Those are my two questions. Make sure you listen to my words and you answer the questions in the comment section. Okay, I want the comment section to be full so that when people are coming to watch the video, when they were not there originally, they will realize that no, this video is very important and people were actually following up the video. Okay, the carbon atoms in the following compounds exhibit different hybridizations. We have compound A, compound B, and compound C. Using letters A, B, and C, select the compound in which the carbon atoms exhibit only. First one, sp3 hybridization. Clearly compound B, right? sp3 hybridization, it means that you just have single bonds all through. Let's go to sp2 hybridization. sp2 means you have double bonds, so normally it's compound A for sp2, but since the equation is having sp is now triple bonds all through, so we have this. So the carbon atoms here, this carbon is bonded to this carbon by triple bond, so the two carbon atoms exhibit sp hybridization. Now this carbon is bonded to this carbon by single bond, so the two carbon exhibit sp3 hybridization. And this carbon here, wait, sp3 hybridization is B, right? Yes. Now this carbon is bonded to this carbon by double bond, so the two carbons exhibit the sp2 hybridization. So sp3 hybridization, we have compound B, and sp2 hybridization, we have compound C. No, sp hybridization, we have compound C. Next question. Write down the structures of two isomers with molecular formula this C4H8 that will not decolorize bromine water at room temperature and pressure. Now C4H8 is butene, okay, and all alkenes will decolorize bromine water. The presence of the double bond as a test for unsaturation. But now, can we write an isomer that will not decolorize bromine water? Yes. So that isomer should be what? An alkane. Okay. So I'm going to write one of them, and you're going to look for the other one. So this is the first one. Clearly, when it is square-like, okay, there are 4 carbon atoms, C, 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 and C, and 8 hydrogen carbons, 2, 4, 6, 8. All the bonds here are single bonds, and when all the bonds are single bonds, it's an alkane molecule. okay, and when you're an alkene molecule, you cannot decolorize bromine water because there is no double bond. You are actually saturated. Alkenes and alkynes are unsaturated. So this is a compound I have named. So the next compound, you are going to name it F. This compound, which compound is this? Yes, I want you to answer which compound is this. Think about it. Okay, anyways, if you got your answer, this compound is propanone. It reacts with 2,4-dinitrophenylhydrazine to give an orange precipitate. What is the name given to this type of reaction? It's a condensation reaction. Okay, water is going to be produced at the end of the day. Now, Roman 2, write the equation for the reaction between 2,4-dinitrophenylhydrazine and propanone. This propanone. All right, so I start by taking my propanone. Okay, I react it with 2,4-dinitrophenylhydrazine. Here is the formula of 2,4-dinitrophenylhydrazine. Okay, now what am I going to get? Now, since this is a condensation reaction, water is going to be formed. And how will the water be formed? First of all, let me the reaction condition is warming. Okay, now for the water to be formed, this was going to happen. The O here, okay, will combine with this H2 to have H2O, which is water. So when it does that, this double bond which is here, this is a double bond written here. So this carbon and the two methyl groups will just attach themselves here. So I just have this. That's what I'm going to have. And then now the resulting water is going to be formed. So that's just a paraphrase of the reaction mechanism. So the H2 from this guy here will combine with the O from the propanone to give us water, and then it's kind of, you're going to rotate. This double bond will just attach itself to nitrogen, and then the CH, in fact the remaining compound will remain unchanged. So this portion of the compound, this portion will remain unchanged. Okay, this portion will remain unchanged. So here is a portion here, so it's just going to attach itself onto the double bond. Is still going to be there. Voila, that's it. So here's a double bond, right? Here's a double bond, and here is also the double bond. Then the H has combined with the oxygen, and we have water. All right, so that's a reaction. Okay, compound G. This is the last question. Finally, we are coming to an end. When hydrogen bromide is bubbled through propene, 90% of the products obtained in 2-bromopropane, while only 10% is 1-bromopropane. This is supposed to be is not in. Roman 1. Why is 2-bromopropane obtained with a higher yield? Clear. Markovnikov's rule. What is Markovnikov's rule saying? Now, Markovnikov's rule is saying that when we add an asymmetric or an unsymmetrical reagent to an asymmetric alkene, the hydrogen atom of that reagent will attach itself to the carbon atom of that alkene containing the highest number of hydrogen atoms. Okay, so the second question is saying that we should state the specific type of isomerism that will relate the two compounds above. What is the is position isomerism, right? Because we have 2-bromopropane and 1-bromopropane. The next question is write the reaction mechanism. So I'm going to explain the Markovnikov's rule perfectly here from the reaction mechanism we are going to be writing. So first of all, I begin with my propene, that's the alkene molecule. Now we need to add hydrogen bromide. Okay, so the Markovnikov's rule is saying that the hydrogen atom from the reagent, okay, will attach itself to the carbon atom of the alkene with the highest number of hydrogen atoms. Yes, that's what it is saying. That's the hydrogen atom of the double bond specifically. So here there are two carbon atoms of the double bond. Which one has the highest number of hydrogen atoms? Is this carbon atom here. So this hydrogen atom of the reagent will attach itself to this carbon atom, and this becomes CH3. Then the bromine molecule now will definitely attach itself to this other guy. So how will the mechanism be? First of all, for this hydrogen to leave, and also for the bromine to leave, this hydrogen, for the hydrogen to leave, is supposed to lack electrons. Okay, so the bond between hydrogen and bromine will first of all be broken, and since bromine is more electronegative, the electrons are going to be pulled towards bromine, and they are now going to acquire slightly positive and slightly negative charges. Okay, now the next thing is that according to Markovnikov's rule, this hydrogen atom of the reagent will need to come and attach itself to what? This carbon atom here. Basically, there are electrons here. Okay, this is a double bond. It contains electrons. So since this man is slightly positive, then definitely is going to be looking for an electron-rich center. All right, looking for an electron-rich center, you need to come to this double bond. Now that double bond is going to be broken to a single bond, and once it is broken, this hydrogen atom here will just attach itself, and in fact, when that bond is broken, this carbon atom becomes slightly positive, right? This carbon atom becomes slightly positive, and basically the hydrogen atom, according to Markovnikov's rule, will need to attach itself to this carbon atom here, since this carbon atom of the double bond has the highest number of hydrogen atoms. There are two carbon atoms of the double bond, the one in green and the one in white. The one in green has just one hydrogen atom attached to it, and the one in white has two hydrogen atoms. So the one in white has the highest number of hydrogen atoms. So according to Markovnikov's rule, the hydrogen atom of the reagent will come and attach itself to this carbon atom of the double bond having the greatest number of hydrogen atoms. That's why it is attaching itself to this carbon atom having two hydrogen atoms here. So when that is done, we are now also going to produce this Br minus, and again this Br minus will need to attach itself now to this slightly positive carbon here as kind of a substituent group. Okay, and then we are going to get 2-bromo, that's it, 2-bromo-propane. Okay, so that is the that's the reaction mechanism. Okay guys, finally we have come to the end of this video. 1 hour 7 minutes video. Thank you guys for watching. If you have been here from the beginning, thank you guys for liking the video. I know that you have liked, you have commented so much, you have subscribed, and please share the video. Very important. There are many guys out there who are facing difficulties with chemistry. Okay, and the purpose of this channel is to help us increase and have a good vocabulary in chemistry. So guys, make sure you like the video. A very great motivation. You comment. When you comment, I'm going to know that actually people are not just watching, they actually like they actually like the video. And liking the video means, commenting on the video means that actually the video is really good, or actually the video has helped you. Even if it is not really good, at least the video has helped you in one way or the other to understand some things. Okay, your comment will also help us to know how to explain better in other videos to improve on our explanations. Okay, so guys, make sure you share the video with your friends, because I know that there are guys out there struggling with organic chemistry, and once you share the video and they visit the channel, they are going to be having updates from the channel when other videos are going to be posted. Thank you guys for watching, and see you in the next video.